Okay, so today we'll have a lecture 3 of the linear logic class, and the title of the lecture is Harmony, which everybody of course wants. So that's our way to think about the propositional connectives, to make sure that the rules for using them and proving them are actually sort of make sense together. We'll go through a couple more examples if we have time. A couple of announcements. The assignment one will be out soonish, maybe today, maybe tomorrow. I'm partway through the lecture 2 notes. The lecture 1 notes have been posted. If you have any comments, you should send me an email. There are some exercises on there. So I will assign some subset of these exercises as part of assignment 1. Okay. Of course, you're welcome to do them all if you want to, but you don't have to. So the hangout last week seemed to go pretty well. People came in and out over the span of the hour. This current week, I'll actually be in Philadelphia at Popple. I'm not sure if I'll be able to have a hangout from there effectively, simply because it's unclear what kind of internet connection and so on we'll have over there. So I will try, and if it doesn't work, then I'll try to arrange for another one next week before the assignment is due. So originally it said the assignment was due Monday, but a number of the students are also at Popple and asked me if they could have an extension. So I'm not going to hold you to the deadline, to the Monday deadline. You can actually hand it a little later if you want. Okay. So let's get started on the connectives. So remember we had what's called a sequent. And we came to sequence because we wanted to be more precise about the inference rules, or we wanted to extend it in particular to have hypothetical inference rules. Inference rules which depend on other rules, and that was kind of weird. So if you remember, the example for that was if wishes were horses, beggars would ride, and we couldn't represent that. And so a sequence looks like this. So we have A1 is ephemeral through AN is ephemeral. And over there we have C. And the way we think about these things here as resources. Okay. And as before, they get consumed as we're doing our logical inference. And the C over here is our goal that we're trying to achieve. So it's a little bit different from the usual way we think of a sequent if you do classical or intuitionistic logic, because these aren't just arbitrary assumptions that we have, but they actually get consumed in the process of inference. And this is not something we're trying to prove, but some goal that we're trying to achieve with the resource that we have. And so we usually abbreviate the resources as delta in order to make it quicker to write. And also because we can always tell where something is, either on the right or on the left, we don't usually write the judgments, just to make it easier, quicker to write. Okay, it's implied by the notation. By the way, this sequent calculus is a version of the original sequent calculus by Gensen in this paper from 1935, which he published, which was part of his PhD dissertation. And of course, it was not linear at the time. He gave a sequent calculus for classical and intuitionistic logic. But he was very careful with the rules. You can kind of see that the same idea that he applied also work in this context. Okay. So we had two principles, okay, that were connecting resources and goals. And these two principles will be guiding principle as we look at the connectives. The first one is the identity rule. Okay, so this is the identity rule. And I'm going to actually index it with the proposition that the identity rule is applied at, just to be very clear about that. Okay, so if I have a resource A, I can achieve the goal A. Pretty obvious, should be the case. Otherwise, there's something wrong in the balance between resources and goals. And the second one goes the other way. It says that if I can achieve A as a goal, okay, then I can go ahead, consume delta, and get my goal A. And then I assume it in order to achieve C, then if I put the two resources together, I can achieve goal C. Okay. So this is the cut rule. And again, I'm going to write as an index the proposition A at which the cut takes place. Okay. So these two things show, these two rules kind of write down as rules without reference to any particular propositions, okay, or propositional connectors, I should say. The idea that resources and goals are sort of work together. So if I have a resource that should achieve the goal, if I can achieve the goal, I'm licensed to assume it as a resource. Okay. Okay, so that's also the idea behind the way that we define connectives. Okay, so for each connective, I'm going to explain to you how to use it as a resource and how to establish it as a goal. Okay, so I'm giving you both of these pieces of information, and the two have to fit together in order for these principles here to be correct. Okay, so the first one we had is tensor, so I'll just remind you quickly of that. So A tensor B, which is called simultaneous conjunction because I want A and B to be true in the same state while I'm trying to derive C. Okay, then I just get A and B separately. Okay, and that's called the left rule. So what happens in the left rules in the logic define how to use, okay, a particular resource which is compound. So think of it as just like a package which is A and B in it. By applying this rule, we unwrap it and we get A and B separately. Okay, and the right rule, which I'll write over here, if we're trying to show that A and B can be true in the same state, what I have to do is I have to be able to show A and B. Okay, but while I do that, I have to split up my resources because I'm not allowed to duplicate them. I have to use them exactly once. So I put some resources here and some other resources here, and then I combine them together like this. Okay. Okay, so that's the tensor right rule. And so the right rule for each connective shows you how to actually prove it, how to establish the goal A tensor B. Let's do it also for implication. Okay, so the right rule for implication says actually, somebody can tell me, how do I achieve the goal A linearly implies B or A lolly B? What does it mean intuitively? Yeah?
Move A over the context.
Right. So that's the formal way to do it. What it means intuitively is if I had resource A, I could achieve B. So we put ourselves into a position where I have resource A, and now I have to show that I can accomplish B. Okay. So A linear implies B means with resource A, I can achieve goal B. Okay. So the corresponding left rule, if I have A arrow B as a resource, I'm trying to achieve C. How do I use that resource? Okay. We have to establish a proof of A. Okay.
Some set of resources delta.
Okay. With some resources delta, I have to establish A. And then what can I use during the proof of C?
Some other delta prime with B.
Okay, so the remaining resources delta together with B. And then I need delta and delta prime together with A implies B to get C. Okay, so I use the fact that I can go from an A to a B. By getting an A, I can get from an A to a B, consuming this as part of doing that inference, and then assume the resource B into my context. Okay. Okay. So let's make sure that these two things work together. And the way we check that is two things. Okay. Namely, the things that correspond to these two rules. Okay. So if I have A implies B as a resource, I can achieve it as a goal. Okay. So the question is, if I have A implies B as a resource, then I can achieve A implies B as a goal. So that should be the case. Okay. So without using that rule, how would we actually go about showing that the rules that we have for implication are good enough so that if I have this resource, I can achieve this goal? So if we disallow the use of the identity, which of course would be pointless, okay, there's only two possibilities, yeah?
So you first need to show that that's A here implies B and A. That's M, so B.
Okay, so we use the right rule. Okay.
And now you can get that straight from the left rule.
Okay, so now I need to use the left rule. Whenever I use the left rule, I have to prove A over here. And then from B, I have to prove B over here. And I have to decide how to divide up the remaining resources. Some have to go here and some have to go here. It's pretty obvious it has to happen here, right? This A, which is one of my remaining resources, goes over here. And nothing else besides the B goes over here. And then this is the identity at a smaller type. And this is as well. Okay, so another way to say this is that the identity at the type A linearly implies B can be reduced to the identity at A and B. Okay. Okay, so the rules work together well enough so that if I have it as an assumption, I can get as a goal. Now I still need to check the opposite, okay, which is I need to check that I also can take a cut at a compound proposition and reducing it to a smaller one. Okay, so let's see, I'll make room over here. So I need to check that if I have this and I get okay, and so this one was inferred by the right rule. And this one was used by the left rule. Okay, so what do I need to do here to complete this? So I need to consider all possible right rules that can be applied here to infer this, and all possible left rules to use this, and make sure that the use and the proof of it is the same. But I actually have a slight problem here, right? Because I need to split the resources, and I don't know how they're being split. And I only wrote delta prime. Okay. So what I need to say is, well, this delta prime actually consists of two things. I'm going to write it delta prime and delta double prime. And so then here in the conclusion, I really have delta prime and delta double prime. Okay. And delta prime was used to prove A, and delta double prime together with B was used to prove C. Okay. So now I have to show that I can actually eliminate that A implies B. Okay, I can actually reduce it to a cut at a simpler type. And how would I do that? How would I reduce that? Anybody see how that works? This is the left rule here. Okay, so first we do a cut at A. So this with this over here. So we have delta prime proves A, delta and A proves B. So we do a cut at A to get delta together with delta prime prove B. Okay, so that's good. And what next? Yeah?
Your cut at B?
Cut at B with this thing over here. So we have delta double prime together with B. Get the C, and then we get delta prime, delta double prime proves C by doing a cut at B. Okay. So indeed, if we introduce, we have this achieved as a goal with some kind of proof here that introduces it on the right, and here that uses it on the left, then the two can offset each other, and then we can eliminate that and just do a cut at smaller types. Okay. Okay, so actually it turns out, we'll get back to this a lot, but this transformation from here to here is actually what's called a proof reduction, because we're using this proof, which uses cut at a complex type, and reducing it to a proof which uses cut at a smaller type. So this is called a reduction. And proof reductions will be at the heart of thinking about how linear logic relates to computation. Because you can actually think about these kind of reduction, it turns out, as kind of computation rules in a programming language. Okay. Even though at this point this may be very non-obvious, okay, but I hope to explain in such a way that it'll be clear how these kind of reductions can be the base for computation. Okay. In order to do that, we need to sort of develop first a programming language. It'll take me a little while to do that, so we won't do that right away. Okay. But for the moment, we think of these as a justification, as a check, making sure that the rules for the logical connectors actually work together properly. It's probably worth thinking about what happens when these things don't match up. Okay, so a little bit later in the lecture, we'll give some examples of where they don't match up, and we see what the consequences of that are. Okay, because it's well and good to check that these actually work, but we also need to see what goes wrong when the principles don't hold the way you expect them to. Okay, so let's create some other connectives. Okay. One way to think about connectives is that if you have a binary connective like tensor, okay, there should be a null reversion of the same thing, sort of a unit of tensor. So what you expect at the end, okay, let me erase this here to give myself some room on the board. Would be that a tensor, its unit, I'm going to write this as 1, should be equivalent to A. Now, how would we formalize is equivalent to? What would we have to check that say something is equivalent to something else? Any suggestions?
If without any resources, I can achieve the goal 1.
Okay, so that's correct, but I was asking a slightly different question. Anton, do you have a suggestion?
Maybe you can prove from one, you can prove from the other, and then you wait for one, you can transform it into proof from the other.
Okay, we can do that, but there's a sort of direct way of doing this, which is that we do this, okay, and then we also do the opposite. From A, we can prove a tensor 1, right? And then what Anton suggested is a consequence, right? Wherever we used A, we can use A tensor 1. How? Yeah?
Well, we can stick in the proof for that, the derivation from A to A,
Mm-hmm.
tensor 1.
Okay, so we have something that proves C from A. Now, how do we get from this to a proof that uses A tensor 1 instead? Cut, right? So we cut that with the proof that goes from A tensor 1 to A. We apply cut, and we get a proof that just goes from delta together with A tensor 1 to C. Okay, so as a consequence of proving this, we know that wherever you could have used A, we could have used A tensor 1 instead. And you can see vice versa, right? If we used A tensor 1 somewhere, we can use A instead by using cut using this proof. Okay. So therefore, the two are functionally equivalent, right? We can always use one instead of the other wherever we want to. Can we prove one instead of the other? If we proved A tensor 1, can we get always a proof of A? Yeah, and how do we do that? Well, is it too obvious? Okay. Yeah?
Among the premises.
Okay, so let's say we have proven A tensor 1, and I want to now show that I could prove A also. How would I do that? It doesn't have to be directly among the premises. So how do I prove now that I could get A instead? Cut, exactly. See, there's cut. So we have A tensor 1 proves A. We use cut, and we get a proof of A. Okay. So on both sides, because uses and proofs are the same, right? If I have these two kind of entailments here, then I can go back and forth between these two on both sides, right? If I have this, I can get to A. If I've used this, I can use instead A, and so on. So I can go back and forth between A tensor 1 and 1. So these two are logically equivalent. Okay. Okay, so the question is, what is 1? And I think Pavonia has already answered that. Okay. So, but let's try to see, how do I use 1 while I'm trying to achieve C? Okay. And be guided by the left rule for tensor. Okay. Think of it as what would be a version where you have a tensor with 0 components, right? A nullary version of a tensor. So what would that suggest for the left rule? Yep. Okay. It's not a very useful resource. It just goes away. Okay. Now, going away turns out to be useful sometimes. Okay. As we'll see a little bit later in the lecture. And how do I prove it? What do I need in order to get 1? Nothing at all. Yeah. I don't need any resource. Okay. So let's look over here. You see that's consistent. So here, if I have a tensor, and I think of it as a tensor of 2 things, I get A and B. If I have no things here, this is just 1. There's nothing here, so just get delta. Here, I have a tensor of 2 things, and I get 2 premises. If I have a tensor of no things, I would get no premises. Okay, so I don't have one over here. And so here I have 2 deltas, which 2 sets of resources go to the 2 premises. If I have no premises, this would be empty, so I get this. Okay. Okay. And are the 2 in harmony? Okay, what do we need to check? So we need to check first that from 1 I can prove 1. Okay, so the question usually is, which rule do I apply first? Well, I can't apply this one because the context is not empty. So apply 1 left. From empty I can prove 1, and then I prove 1 right. Okay? And the other one would say if I have a cut that uses 1, so I have from delta I can prove 1. And delta prime and 1 I prove C. Then from delta together with delta prime I can prove C. So can I reduce this to a cut? This is a cut on 1. This is an identity on 1. Okay. So can I reduce this to a proof that doesn't use 1? Well, not in general, right? I have to think about what's happening here. We always want to match up a right rule with a left rule, right? Correct? That's what we're checking. If I use a right rule to infer this and use a left rule to infer that, then I can reduce it. Okay, so if I use 1 right here, what do I know? Well, I know delta has to be empty, right? Because if it was the right rule, delta was empty. And here I used the 1 left rule. So the premise says from delta prime I can prove C. Okay. So now why can I reduce this? What do I have to reduce it to? Yeah, because delta is empty. Okay, I need to reduce it to delta prime prove C, but that's exactly this premise over here. Okay. So a cut at 1 just reduces directly to one of the subproofs in this case. And the identity at 1 can also be proven directly without. And that makes sense because we're taking a cut of a compound formula and you're reducing it to a cut on smaller formulas. And 1 doesn't have any components, so it just kind of has to disappear because we can't create any new cut. But fortunately it does. So the reduction here just takes that proof and returns it here. Okay. So the left and the right rule, the way we've written them actually makes sense together, which is good. Okay. So let's try to see what happens if we have some rules that don't actually work together. Okay. So so you should be able to verify these laws now. Okay. Actually, let's do one example. How about this one? So A tensor 1 proves 1. How do we prove that? A tensor 1 proves A, I mean. Yeah?
So you need a comma 1 to tail A.
Okay, tensor left, a comma 1 proves a. All right?
So you need A to tail A.
All right, and you use the 1 left, and then a entails a, and that's the identity at a. Okay? So these things are usually easy to check, and I'll give you the opportunity to check these things in the homework. Okay? Okay, so now let's actually mess up the system a little bit. Okay? So the tensor left rule here says that from A tensor B I can get A and B. So I'm going to replace this by two rules. One says if I have A tensor B and I try to prove C, I can get A. And the other rule would say from A tensor B, I can get B. Okay? So in ordinary logic, right, if you have a conjunction of two things, you can get the components. You can extract them out. Okay? Okay, so these were two alternative left rules. I'm hesitant to even write it down because they don't make sense. But we have to discover and see what was wrong. Okay? So intuitively, why doesn't this make sense? Yeah?
Well, when we use it, we're throwing away all knowledge of the other component. So if we eliminate it towards A, then we have no further knowledge of the fact that B was.
Right. So our interpretation of the sequence is tight in the sense that every one of the resources has to be used exactly once, right? So if you put together A tensor B, we have an A and a B. We put them together. And then we kind of drop the information about B from the sequence. So something has to go wrong somewhere. Otherwise, our test is really not worth anything, right? Because these rules are wrong because it dropped resources on the floor. Okay? All right, so actually, which thing goes wrong? Is it the identity or is it the cut principle? Okay, well, let's see if you can prove, yeah?
I think the identity should go wrong.
Okay, so let's try that. So we have A tensor B, and we're trying to prove A tensor B. Okay. So can we apply the tensor right rule on this? Well, the tensor right rule would require us to split our resources. Okay. So we only have one resource, which is a tensor. So we have to put it either to the left or to the right. So one possibility would be to put A, B, to put it over here, say. And then this part works out because we can extract A, and from A we can get A. So this side is okay. But obviously we're stuck on this side because we have no resources here, and from that we can't get B. Make sense? So the right rule doesn't work. So the only thing is we can do the left rule, right? Okay, well, which one? Well, we have to decide, right? Because this thing disappears when we apply left rule to it. It goes away, right? Because, so let's take this one. The other case should be symmetric. Okay, so this case we can only apply the right rule. And so we have to put A over here to be able to prove A. And over here we're again left with B. Okay, lonely. Okay, unable to prove it. Okay. So that was mean is basically that these rules, taking them the way they are, would not allow you to prove the identity. Okay, so our test does fail. Okay, but what kind of consequence could we get from having these rules besides the fact that just our test fails? So in fact, if the test fails, it'll have some consequences in our interpretation of the judgments. So any idea what property of we might be able to prove here if we had these two rules instead the one that we wrote?
We could make the number of resources grow.
Okay. So the idea is that we might be able to make resources grow. Okay. So how would you write that down? Okay, so I'm going to translate your statement the following way. Let's see if it makes sense. If you can prove C from delta, then we can also prove from delta and A. Okay. By the way, this rule here has a name in ordinary logic. Does anybody know what that is? Yeah?
Weakening?
It's weakening, right? Okay, so in linear logic, weakening should definitely not hold, because we say that we must use every resource exactly once. And obviously, this resource is not really used in this proof. So this should not be. If we had this rule, right, then we would have invalidated our whole interpretation of what the sequence actually means, because we're not using the resource A. And we do want to be precise about the resources, which is the whole point about linear logic. So, actually, I should have checked this before lecture, but I'm claiming now, okay, that if we had these rules, okay, because we can drop B on the floor, we should be able to show that this is the derived rule. And that would basically say that our whole discipline of linear logic is destroyed. Okay. So let's see if we can come up with a proof of this derived rule. Right. Okay. Okay. So we know from delta prove C, and somehow we want to prove that from delta together with A, we can prove C. Yeah, Anton?
You start by inserting the identity into the context.
Up here, you mean?
Yeah.
Okay, so we add the identity into the context. So that's the one left rule, okay?
And using like one of the answer left rules
Yeah?
to like just add A onto one.
Okay, so we now use, let's say this one here. So we get delta n1 tensor A proves C, okay? And that would be one of these tensor left rules, okay? And then?
Get rid of one.
Okay, how do we do that?
By whatever proof it's just it's equivalent to A. By whatever proof it's just
Okay, we had to prove that this was equivalent to A, so how do we use that proof now? Cut, okay. So from, okay, let me get rid of this. A, we can prove 1 tensor A. And so then we use cut to show that from delta and A, we can prove C, okay? Okay, so we could use this exact proof here, okay? No, we couldn't. I didn't write the other direction, okay? Can we get from A to 1 tensor A? Let's just fill it in. How do we do that? Which rule do we apply? The right rule for tensor. We have to split our assumptions. We prove 1 over here and we prove A over here. Where does A go? Well, it shouldn't go here, so we keep this empty and it goes over here. This is now the identity and this is 1 right. Okay? Okay, so this is the proof that shows that if we have delta arrow C without anything else, we can delta comma A prove C. Okay. Yep. Yep.
But as you said, if you replace the original rule with these two rules,
Yeah.
then identity will fail.
Right.
Then how can we use identity here?
Okay, so identity for all formulas except the ones that have tensor should still be the case, right?
Yeah, but then the theory doesn't hold for the case that A has tensor.
Okay. Okay, that's fine.
Well, you can still use the identity rule.
Yeah.
Identity is a primitive on proposition.
So-
Just rule with the other rule, but
So-
you use the
Yeah, so the way I've written here so far, these are rules, right? But we can't verify that identity at more complex propositions can be reduced to identity at smaller propositions. Okay. And similarly with cut, right? So this is identity at A, and this is cut at 1 tensor A. Okay, so I can still use those rules here because I haven't. But there's a technical distinction. In the sequence calculus, we have to find it here, and the way that Gensen defined it, cut and identities are rules. Okay. Then there's also something called the cut-free sequence calculus, where they are not rules, and we'll come to that later. But for now, they're rules, so we can make these inferences. Okay. But our test nevertheless fails. And in fact, the consequence of that is very bad. So we don't get a contradiction as such, right? So if you work in intuitionistic logic and your tests fail, you might get situations like, you can prove a contradiction. In this particular case, we cannot prove a contradiction, but we get weakening as a consequence, right? And weakening is something you definitely did not want because we have linear logic. Okay. All right, so anyway, so this basically says that, well, in this case, our test failed and we got a bad consequence. Okay. So you'll be able to explore some other bad consequences when certain test fails in the homework. Okay. But I want to move on and develop some other logical connectives to express some more situations that we didn't really talk about before. So what we have so far is linear implication and tensor, and we also have unit. Okay. Now with these, we should be able to do all the inference rules we have written so far. So the inference rules look like this, if you remember. For example, we had several premises, so A1, AN, and then we had several conclusions, B1, BM. Okay. If these are all ephemeral, how would we write this down as a formula? What's the intuitive meaning of this as a formula? Okay, so these premises have to be true at the same time, in the same state. So A1 tensor AN, okay, implies that B1 tensor BM. Okay? So we can take any rule like that and express it instead as a proposition, okay, in the logic, because we now have enough connectives to do that. And why did I need one for that purpose? Yeah?
In case one of them is empty.
In case there's no conclusion or there's no premises, right? So then this tensor here becomes 1 or this becomes 1. Okay. Okay, so now I still can't write all the rules that we've had because what's still missing? Yeah? Okay, so there's choice. We didn't really talk much about that. What else is missing?
Persistent facts.
Persistent facts, right? We had rules that had persistent facts as premises, and we don't have them integrated into our system here. Everything is ephemeral, and so when you think about this as an implication like that, there's no way to represent the fact that it's persistent. Okay. And in fact, even saying that this rule becomes this is not quite accurate. Yeah?
Could you just encode a persistent fact as one lolly the fact?
Okay. Good point. Okay, so the question, this is already, like I said, inaccurate. So the question is, if I have one lolly some fact, does that represent A is persistent? Okay, not quite. And why not? Anybody have a suggestion why not?
If you have it on the right, if you're trying to prove that proving one only A isn't the same thing as proving A persistent. Because you could like consume a resource A to do that.
Okay, so there's that one problem. If you have A ephemeral, in order to make it explicit, and I tried to prove that 1 implies A ephemeral, I would put 1 over here and then use a 1 left rule, and then by identity I would get from A to A. So it could prove that. Yeah?
So one lolly A itself is not persistent?
That's right. So 1 lolly A, if it's an assumption in your context, which would represent the rules that you have, it disappears when you actually use it. Okay? So the implication itself is ephemeral, and the rules are supposed to be persistent. Okay. Okay, so we need some other way to do persistence in this kind of a framework. Okay, and the other thing we need is some kind of a choice. So let me do choice first. Okay. Okay. So what does choice actually mean? Okay, keep these rules here. Get rid of this. Okay, so the idea is that we have a resource, okay, which we're going to write this way. And the idea is we're trying to prove C. We have some other resources, delta. And the meaning of this resource, which A with B, is that you can choose which one you actually want to use in order to achieve the goal. Okay? So somebody gives you a choice between those two things, and you can use either one, but you can't use them both at the same time. Okay, so you have to make the choice which one you use. So that means there's going to be two rules, a left rule. And one says, from A I can prove C, okay? And the other says that I could decide to go ahead with B and use C. Can anybody think of an example? Sort of in the spirit of the examples we already had, where this might make sense? What kind of situation might you want to express? No ideas? Yeah?
Alternate currencies.
Alternate currencies, okay. So what would be that example?
So you buy a chocolate bar for either dollar or euro.
Okay. So how would we actually then express that? So you have a chai bar and you can use $1 or €1. So how would we say that? So $1 gives you that. €1. Is that what you mean? Or did you mean something different?
It's more along the lines of $1 in a choice of €1 that will welcome chocolate bar.
Okay. So $1 choice, €1 gives you, okay. Does that express what we have in mind?
So I think that would be harder because you have to prove that you come up with either $1 or €1, and whichever they want to.
Right. So what this one would mean is that in order to get this, you have to demonstrate that you could come up with $1 or you can come up with €1, right? Because in order to use that, you have to prove that, right? In order to prove that, you have to be able to prove that this, and you can also do that. Okay. How about this? Does that first rendering make some sense? So I want to buy it, and I have the choice between taking this or taking that. If I take this, I have to supply $1 and I get it. This one disappears, right, because that one's gone. Or I can choose this part here, okay, which would be B. This part disappears, and then I give €1 and I get it. So it seems like this would be the correct idea of using a choice. Right, so the vendor in the airport gives you a choice, right? Either you can give me $1 or you can give me €1. Of course, you want to spend the $1, okay, but that's your choice, right? Okay. So that would be an example. So let's go back here and let's see if we can figure out what the right rule for this should be. Okay. So under which circumstances can we have A with B with some resources delta? Okay. So I kind of already talked through it in the second part. So this is the one that makes sense, and this one seems kind of questionable. Okay. It's not what we had in mind. So how do I establish A with B?
You're
Yeah?
going to establish A from what you're given,
Okay, I have to be able to step.
and at the same time you can establish B with what you're given.
Okay, you have to be able to show that you can establish both of them, right? Now that seems weird because we're not supposed to be able to duplicate assumptions, right? Because the interpretation of a sequence is that the resources are used exactly once, but here it looks like we're using them more than once. Okay, so we have to figure out why that's okay. Anybody have an intuitive idea why this is okay? Yeah?
It's basically like saying that when you use an A and B,
Yeah.
you're picking which one of the proofs you're using.
Yep, exactly. Because when we use that, we only use one of the two proofs, either this one or this one. Okay, so we're actually not duplicating anything because I'm not giving you both of them at the same time. I'm only giving you one, and you have to pick which one. Okay, but that exact argument now, let's see how that comes out when I do my test. Okay, my test is that if I have a cut which introduces that, and then another one that uses it, that the two actually work together. So let's check that. So I have a cut between A with B, which was proven from A and was proven from B. And over here I used it. And maybe I used it by using the first part of it. And then I had the cut at type A with B. And then I get delta and delta prime together, I can get C. Okay, so how would I be able to reduce this to a cut at a smaller proposition?
Just don't use delta B.
Hmm?
Just don't use delta B.
We don't use that. We just cut this thing with that. So we take delta proves A, delta prime and A together with C. Then I get delta and delta prime together establishes C. So we just cut this with this. So that's a cut at A. Okay. Now, if this one was the other left rule, how do I proceed then? Well, then I don't use that part here, right? I just use the proof of B. Okay. That's why I need both of them, because I have to account for the possibility that either this one was used or this one was used. And since I have both of them in my hand, depending on which one is required, I can supply one or I can supply the other. Okay. So the two things do work together, but I still have to check identity. So this is and left 1, left 2, and this is and right. So identity says that if I have A with B, I can prove A with B. Okay. So how do I prove that? How do I reduce it to identity at smaller formulas? Well, with these things, I usually just have to figure out, do I use the left or the right rule? Okay. So which one do we want to use first here? The right rule. So we get A with B proves A, and A with B proves B. And now we use the left rule, and then we have identity at A. And here we use the other left rule and use the identity at B. Okay, so identity at A with B reduces to identity as A and identity at B. So, okay, harmony is established. Okay, let's think about the zero-area version of that, or the null-area version of it, just to be complete with respect to our connectives. Okay, so that is called top, and it should have the property that A with top is equivalent to A. Okay, so it's a unit of this kind of conjunction. So what would be the right rule for that? Okay, so the way you think about this is you take the binary rule and you try to see what would happen if the conjunction had no components to it, right? The nullary version of it. Okay, so what would be the nullary version of this? Yeah? Okay, it would be delta entails top. I'm starting to run out of room. Okay. Okay, no components of the width, no premises. And what would be the left row? So this width here has two components, so we have two left rows. If it's a nullary version of it, it has 0 components, so how many left rows? 0. No left row. By the way, it's always good when you write down a system like this to actually write down if you have no rule of a certain type explicitly, just so it doesn't look like an oversight. Okay, just to be very explicit about it. Okay, so this is the right row and we have no left row. So if we have that as a resource, we can't actually use it. Okay, and so top consumes all resources. Okay, so that's a little bit of a scary thing because we're supposed to use all resources all at once. But it's okay because if somebody has top, okay, they can never actually use it. Okay. All right. So, okay, so that's a width. Okay. There's also a disjunction here, A or B. Already, this width has a kind of an idea of an A or B, right? So, because the example that we have, you can buy this if you have $1 or you have €1. You can buy the chocolate bar. Okay. So there's some kind of an or because it involves a choice, but a choice that you can make. Okay. Now conversely, there's also something called an external choice somebody else can make. Okay. Okay. So. So if you have a resource, and that's written as A plus B, A plus B, while you're trying to achieve C, you don't know what you're going to be getting. So if you want to be sure that you can do C, you want to be able to do it if you get an A, and you also want to be able to do it if you get a B, because you don't know what's going to be delivered to you. So therefore, we have to take delta and A together, and we also have to show that we can get it from B. Okay. Now we don't have to worry about the fact that delta is duplicated. Intuitively, why? We're not really duplicating resources here because we're only ever going to use either this one or this proof, right? Because whoever promised to supply is A or B, they're either going to give you A or they're going to give you B, but they're not going to give you both, just one of them. So either you're going to use this part or that part. Okay. Okay, so we need to figure out what the right rules are that correspond to that. So that's the or left. Okay, any candidate for a right rule? So if your obligation is to produce an A or B, how would you satisfy it? Or how could you satisfy it?
Give me an A.
Yes. And the other alternative would be to produce a B. Okay? Okay, and now you can verify that this satisfies all the things that we wanted it to do. Okay? So I don't want to talk through the details of that. Okay. Okay, so let's move on to talk about the persistent assumptions because that's the last piece in the puzzle, and then we're running out of connectives. Okay. Already we have more connectives than ordinary in logic, right? Because there's two forms of conjunction. One is called the simultaneous conjunction, where it's true in the same state. Okay, so that if you have A and B, you get both A and B. And the other one is an alternative conjunction, where you can get either A or you can get B. Okay. In ordinary logic, those things are not really distinguished. Okay, that's because you can use assumptions as often as you want. If there's no restriction on the number of times you use assumptions, then these two things are equivalent. Okay. For example, if you want to get both A and B out, right? You can use this rule to get A, because you can use that again. You can also get B, so you can get both. Okay, and some similar argument holds over there. So in ordinary logic, there's only one form of conjunction. In linear logic, there's two forms of conjunction. Now, there's a debate how many forms of disjunctions there are. The way I'm doing it here in this kind of a logic, there's only one form of disjunction. Okay, but in Girard's formulation, actually it turns out there's two forms of disjunction, and this is one of the points of distinction between Girard's version of linear logic and this version that I'm presenting here. And so we'll talk about that again some other time. But what we'll talk about now is the question on how do we actually model unrestricted resources, okay, or persistent resources. Okay. So what we're going to do this is that we're going to have a new primitive. Okay. So our sequence is going to be changed to something like this. So instead of just saying delta achieves C, we have a second part here which I'll write a gamma, and the gamma contains the persistent resources. Okay, so those are the things I can use as often as I want. Okay, so let's take a look at what the rules need to look like for this. Okay. So the first principle it says is very similar to this rule that I had before. The rule that I had before was this: if something is persistent, then I can get an ephemeral copy of it. And I can use this rule as often as I want because this never goes away. Okay. So now we're doing the same thing. So if I have gamma and one of the things in here is a persistent copy of A, okay, then I have delta and I'm trying to prove C. Then with the rule we'll call copy, okay, I keep A persistent in here and I add a copy, an ephemeral copy of A here, and then I still try to prove C. Okay. So this rule does not depend on any particular type of proposition because it works for arbitrary A and C and gamma and delta. Okay. So sometimes these rules are called rules at the level of judgments because the judgment of A being persistent is related to the judgment of A being ephemeral. And these rules would be similarly rules at the level of judgments because they talk about an ephemeral resource and an ephemeral goal. Okay. They don't depend on what the propositions actually are. Okay. And these other rules are propositional rules because they decompose propositions either on the right or on the left. Okay. So this would be a judgmental rule. Sometimes you see in the literature the name structural rules for it because it talks about the structure of the sequent rather than the structure of the formulas. Okay. So again, here this is just the structure of the sequence is the only thing that's relevant and not the formula itself. Okay. So this is one rule. The question is, how do we establish on the right-hand side the judgment that something, so this would be ephemeral, of course. How do we establish that A is persistent, persistently true? Okay. So now here's how we use that something is persistently true. How do we establish that something is persistently true? Any ideas? Okay, so the idea would be to require that if require this thing, okay, the set of ephemeral resources to be empty in order to establish that A is persistently true. We only use the persistent facts, okay, and from that we show that A is ephemeral, which is a judgment we already had, okay. So the idea is that if we can show it without using any linear resources, okay, then whenever we need a copy, we'll just use that proof that we have here, okay. It doesn't depend on anything ephemeral, so we can actually use this proof as often as we want because it doesn't depend on anything that disappears, and give ourselves a new copy, okay. But the important part is that the proof that A is ephemerally true does not depend on any ephemeral assumptions, because if it did, then we couldn't duplicate this proof in all the places where the copy rule was being used, okay? Because we would be needing as many copies here of an ephemeral assumption as times that the copy rule was applied, because we'd have to plug it in every time the copy rule was being used. Okay. So this thing actually turns out to be convenient not to have this as an explicit rule. Okay. But whenever we would consider A persist on the right-hand side, we just replace it by this. Okay. So that's just sort of a technical device. For now, I'll just leave it there. Okay. Or maybe I should bracket it, saying that we're not actually really considered this a first-class rule. And that kind of a trade-off we'll see a little bit more as we go along. Okay. So this is at the level of judgment. The question is, how do I internalize that as a proposition? Okay. And why do we want to internalize it as a proposition? Well, because in the examples that we had, for example, in the if wishes were horses, beggars would ride, some persistent facts are in there, or persistent assumptions, and we need to be able to qualify propositions that are nested inside as being persistent. Okay. So we do want to be able to express this idea of a persistent judgment also as a proposition. Okay, so we need to have a right and a left rule for it. Okay. So hope that I don't need to refer to these. Okay, so let's look at it. How do I use the fact? Okay, so that I write this as in this way, exclamation mark A. So Gerard called this of course A. Okay, so something which is persistent or true, of course. Okay. And for some reason, common pronunciation for this has been bang A. Okay. So I will probably usually say bang A. But I'm going to write it out explicitly to be clear about this. Okay. Our situation looks like this. I have some other resources delta, and I have as a resource, of course, A. And so the left rule says now that I can now get a persistent resource, and this ephemeral resource disappears in order to achieve goal C. Okay, so now I can use this as often as I want every time copying it, right? So if I have this ephemeral assumption, I can use it exactly once, like all ephemeral assumptions. And this, the parentheses here are like that, of course, because that's a judgment applied to a proposition. This is a new proposition. So I put it into the context here. Now I can use it as often as I want. It just stays around. Okay, and how do I define the right rule? So, okay, when is bang A true in the ephemeral sense? How do I do that? So, bang right. So we want to prove that A is true. Actually, we want to prove that A is persistent, right? Okay, doesn't matter. And how do I prove that? Okay. Okay, so that's wrong because in the proof that A is persistent, we're not allowed any assumptions in delta, right? We have to be able to prove this without using any resources. So this will have to be empty. And then, of course, this will have to be empty. Okay. So what about this delta here? Well, that also has to be empty, right? Because I have to use every assumption, every resource exactly once. If I just dropped it on the floor here, I would not use any of these resources at all. But I'm required to use them, so this has to be empty to start with. Okay. So I can prove, of course, A only if I have no resources. Okay. Or another way to say it, all the resources that I have are themselves persistent. Okay. So if I only persistent assumptions, then I can prove that by proving A from those assumptions. And so that this intermediate step is usually omitted. Okay, so we go directly from proving that, of course, A is ephemerally true to proving that A is ephemerally true. And I'm only allowed to do that if this proof doesn't depend on any linear assumptions, and the overall proof also does not depend on any linear assumptions. No ephemeral resources allowed. Okay. Makes sense? Okay, so I should show you some kind of a version of this checking that the left and the right rules actually fit together. But I don't actually have the time to go in a lot of detail, so let me actually do an example instead. Okay, actually 2 examples, and finish the lecture with those. Okay, so the first one is if wishes were horses, beggars would ride. We couldn't express that before. Okay, now we should be able to express that, and you just have to grant me the quantifier. Okay, so grant me the universal and the existential quantifiers. Okay, so first thing is if wishes were horses, how do we do that? Yep.
Of course, wishes will be horses. Of course, wish will be horse.
Okay, wish, lolly, horse. Okay. I left some room here because the way I actually formulate it was like, of course, if x were a wish, then x were a horse. Okay, now we said the property where there being a horse is an intrinsic property of x, so that should be persistent. How do I express that? I need to put a bang somewhere. Where? Yep. Remember, I underlined that before, and now that underline just becomes a logical connective. Okay. Now the second was then beggars would ride, and how do I do that? Okay, if wishes were horses, then, okay, beggars would ride. How would I do that? Yeah? So remember, I put some weird sort of meta quantifier in there. Okay, so, and there exists a z, such that z is a horse. And that, of course, is persistent. And y would ride z. Okay, and this is, the quantifier has this scope here. So how do we finish this now? We said if wishes were horses, beggars would ride. So there exists something which is a horse and that rides. What kind of conjunction is it? Is it an alternative or a simultaneous conjunction? Yeah, because I want this thing to be horse and being able to ride at the same time. Don't want to make a choice between those two. Okay, that only leaves the question of what happens with y. Okay, for all y. So the scope of that is everything. And then one more thought. And this is always true, right? Because it's a proverb, it always has to be true, of course. Okay. It's always true that if y, beggars would ride. Where do the beggars disappear to? Okay. Bang. For all y, beggar of y, tensor this, proves that. And of course, the property of being a beggar doesn't go away, so we do it like that. Okay, so if this is a lolly, then you'd read it like this, right? Well, that's okay, because it turns out that A tensor B lolly C is the same as A lolly B lolly C. Okay? Okay, so it turns out these two are equivalent. In function programming, this transformation between these two is called currying and uncurrying a function. So if a function which takes one argument gives you back another function which takes another argument, you can package them up into one and pass the pair to the function. Okay. So we could put a tensor here, or we can put a lolly here. whichever way we choose. Okay, so this is your first thing, this is the second thing. Okay. Does that make sense now? Okay, so now we could say it. Okay, before we couldn't. And what was missing before is, well, there was a problem with this quantifier here. And there was a problem with this bang here, and there was a problem with this linear implication on the left-hand side of an implication. Right? We needed to write down this weird thing where we have an inference rule as a premise to another rule. But inference rules are turned into implications, persistent implications usually, and so we could express it that way. Okay. Okay, let's do one more example. Actually, two more examples. One thing I found on the internet, okay, like everything useful, right? Okay. If I had a nickel for every time I had a nickel, I would have 2 nickels. Okay. Okay. Independently of whether it's meaningful or not, well, actually, it is meaningful. It might be false. Okay. So how would we say that? If I had a nickel for every time I had a nickel, I'd have 2 nickels. Okay, let's break it down. First time, if I had a nickel for every time I had a nickel, how would I say that? Yeah?
Well, do you want to eat your first nickel or not?
Well, yes, I mean, that's implied, right? Well, you don't eat it, but yeah. Not literally, yeah. Nickel, lolly, nickel. But I said for every time, if I had a nickel for every time I had a nickel.
Oh, of course.
Of course. Okay, I have a nickel for every time I have a nickel, okay? And then I would have 2 nickels. How do I say that? I have 2 nickels, right? So that. Okay, so if I had a nickel for every time I have a nickel, I would have 2 nickels. I think you'll find this hard to prove, okay? But that's what he said, right? Okay? So that's due to anonymous. It's a good thing he says anonymous. He or she, I should say, says anonymous. Okay. Okay, last example. This is the food example. Okay. So linear logic originated in France, right? And in France, there's this tradition where you buy, when you go to a restaurant, you can order a la carte or you can order a whole menu at once, okay? Which comes with several courses, which are all kind of tied together. Okay, so let's say this is the American version of it, okay? We pay $50 and what do we get? Okay, so for the first course, we get a choice between soup or salad. How would we say that? We get the choice between soup or salad. Soup with salad, right? Okay. We also get, okay, let's say either lobster or beef. So lobster or beef. Or if we spend another $20, we can get both. How would we say that? Surf and turf, okay. How do you say that? Well, not quite. Because you have to spend another $20. Where are those?
You can put a extra $20 on the right side of the left side of another application.
So $20 implies, and I have to choose either this or this or this. So there's another within here, right? So I can choose either getting the lobster or the beef, or I get surf and turf if I pony up another $20. Okay. All right. So then, next thing either going to be, let's say, either peas or fennel, depending on the season, okay, as my vegetable. How would I do that?
The chef chooses,
Yeah,
so you use a plus.
yeah. So either I get peas or I get fennel, okay, but I can't choose. Somebody else, maybe the chef chooses, depending on what's in season, right? So this is a plus. This is my choice. This is with, okay. Then I get unlimited coffee. This is definitely not France. How do I get unlimited coffee? As much coffee as I want? Of course, coffee. Okay. And I get this together with optional cream. Maybe cream, maybe not, depending on how I like my coffee. How do I say that? Cream is optional. Yeah? Cream with 1. Okay, so this says even if I don't get any coffee, right, I could still decide to get cream. Okay, not unreasonable. But I can get as much coffee as I want, including none at all. Okay. Okay. And anything else I should get with this particular menu? Dessert? Okay. Okay. So let's say either you can get cake or you can get a $5 refund if you don't take it. Okay. How do I do that? How do I get $5 back? Yeah. We don't have minus, unfortunately. And unfortunately, I took negation away from Gerard. Okay. So you can't do that either. How do I get $5 back? Yeah. Okay. Were you going to say the same thing? With 5?
So if I only have $45, I can't get anything. If I only have $45.
Yes, very true. If you have only $45, you can't actually get this menu. Yeah. And this is another thing, right? We pay before we actually start off eating. And here before the thing, the waiter actually collects the $20, right? So it's more like a cafeteria menu, right? So, okay, modulo those little abstractions. Okay, this is our menu here. Okay. So we actually need, it turns out, to say some interesting things, we need a fair amount of the connectors that we have. In particular, we need the with, we need here the disjunction, the alternative conjunction, the simultaneous conjunction, okay? And we need money, of course. Okay. All right, so on Wednesday, I'll be at Popple, so there's no lecture. And like I said at the beginning, I'll try to get out the homework assignment and the lecture notes. And then on next week, we'll start to, you'll do some more examples of this type, okay, in your homework. And we'll start to study the structure of the proofs in some more detail than we have so far. And have some examples on how we use proofs. Okay, so that's starting next week. Any last questions? Okay, see you Monday.